So finally, in this lecture, I would like to tie this in with the P versus NP problem. Now we are relying on a difficult problem for public key cryptography to work. That's listed here as decryption of a message with RSA requires the computation of D. Recall, this is the multiplicative inverse of E modulo P minus 1 Q minus 1. Now, as the public key, N and E is announced, but P, Q, and obviously D are withheld. You do not announce them. And a malicious third party would need to find P and Q from N and then compute D to be able to decrypt the messages. Okay, so in essence, RSA algorithm relies on the difficulty of integer factorization, or rather prime factorization. On the other hand, there are also other cryptographic schemes, such as Diffie-Hellman key exchange and algebraic encryption. They rely on the difficulty of the discrete logarithm problem. If you remember, we mentioned this, and I have stated that we do not, as of today, have an efficient algorithm for the discrete logarithm problem. Again, if you select the values appropriately, meaning large enough and satisfying certain properties, which we will not go into, then it's practically impossible to solve these problems. Okay, so this means your algorithms are going to work in practice, which they are. Now, maybe a small detail to point out here. In general, people use private key cryptography in communications, but they use public key cryptography to exchange keys. So one algorithm for key exchange is Diffie-Hellman key exchange. If you are interested, you can look it up. It's another very good application of modular arithmetic and prime numbers. But in general, that's the approach here. You exchange the key, the private key of your communications using a public key cryptographic algorithm. But then when both sides have the private keys, you continue communications using private key. Now, the question is, what happens if it turns out that P equals NP, which means somebody comes up with an algorithm, a polynomial time algorithm, that actually solves NP complete problems? In this case, remember, it will be the case that P actually equals the class NP. Okay, so what happens then? So most people would answer this as, okay, we will not be able to use RSA, we will not be able to use this cryptographic algorithms that are based on the difficulty of either integer factorization or discrete logarithm. But the answer is more complex than that. Simply put, we don't really know what will happen, because it really depends on the precise efficiency of the solution. Because you see, when somebody declares, okay, I have found a polynomial time algorithm for this problem, it's just a class. It's a polynomial class of algorithms. It doesn't really tell you how much time exactly it will be required to actually obtain the result. Let me give you an example. Take matrix multiplication problem. How would you do it? On paper, you would just go element by element, multiply them, add them together, etc. So you need to do 3 passes on the entire thing. You have 2 matrices, n by n multiplied by n by n. So in general, iterative multiplication is in the order of n to the power 3. On the other hand, we have Strassen's algorithm, which instead of 8 multiplications, it requires 7 multiplications for 2 by 2 blocks, let's say. And the complexity of this algorithm is in the order of n to power 2.80. However, iterative algorithm is actually faster for n smaller than 100. So if your matrices are smaller than 100 by 100, then it's not really better to use Strasson's algorithm. So it's in a better class. So asymptotically, Strasson's algorithm is better. But if the input size is small enough, it doesn't perform better than the iterative algorithm. Let's go one step further. The fastest, the theoretically known fastest matrix multiplication algorithm is actually based on the Coppersmith-Winograd algorithm. And we also have a variation due to Williams. And it's in the order of n to power 2.373. Well, this even looks much better than Strasson's algorithm. But you see, these algorithms are in a class that we call galactic algorithms. Essentially, this means that asymptotically they are better, yes, but the threshold they become better is so huge that in practice we will never use these. Okay, so you see Strasson's algorithm is better if the input size is larger than 100. And it's even more dramatic with these algorithms, the Coppersmith, Winograd, etc. The threshold for these algorithms to become better than the iterative algorithm is so large that we will never use them in practice for actual matrix multiplication. So for instance, let's say somebody comes up with a polynomial time algorithm for prime factorization of integers. What we need to know is the actual amount of time required to factor out the prime numbers that we use in practice. So meaningful real life problems. It could be the case that, well, you know the definition of big O or big theta, for instance, when we say f of x is big O g of x, what we are essentially saying is there are numbers, let's say k and c, so that when x is greater than or equal to k, you have f of x less than or equal to c times g of x. Now, in practice, this k could be very large, so that it's a galactic algorithm, like in the order of 10 to the power 1000, which is not really useful at all. Or the c value could be so large that it's impractical actually to use it. It's probably the actual computation time is very large. Okay, so if somebody comes up with such an algorithm, we will have to use the actual algorithm to make a decision on whether it shatters RSA or not. So the answer to this, what happens if it turns out that P equals NP, it depends on the precise efficiency.